Okay, today's lecture is on implementation, the process of actually ending up with a complete working system. So we're going to revisit some of the things we've already seen, but in a sort of wider, something in a slightly wider context. And a bit of things about management, ongoing management of databases once they've been established. So first of all, I'm going to revisit or look in more detail at design methodologies. So we already met the waterfall model very briefly, and the first half of the lecture is basically going to be running through the waterfall model. Then we can also look at some other design methodologies very briefly, including the sort of idea of prototyping. At this point, I must say that we're only going to scratch the surface of design methodologies for computer applications. People do whole masters, whole degrees on computer design, so we're only just going to be sort of scratching the surface. Then I've got a couple of slides on the roles of personnel, because when you see jobs advertised, they use various terms and things like that. So just an attempt to sort of lay out what these various job titles are and what they do, what these kinds of people do in relation to database design and management. And final little group section on database efficiency. How do we build a database that works in an efficient way and delivers the service that we require? So just this slide just sort of differentiates the difference between design and implementation. Design being the plan, the idea for something that's going to be constructed, and implementation being the entire process of putting a decision or a plan into effect. It's the execution, the physical implementation of things. So depending on, you can either think of design being done first and then implementation of the design, but in a sort of design methodology context, implementation includes generally the design component as well. And we saw that, and just revisiting some of these, so reminding ourselves what design is, the various aspects of design, which come from the sort of system engineering background, the idea of the conceptual design, high-level functions, basic abstract entities, logical design, basically specific entities and their relationships without how it's actually implemented in a piece of software, and then the physical design, the logical design, implemented in specific technologies. Just a bit of a revision there, and we know, and we saw this slide, or a version of this slide previously. If you remember the waterfall model, that's a very basic, simple version of the waterfall model. And we can see that the conceptual, logical, and physical designs roughly match onto various stages overall in the waterfall model of system development. So a lot of what we've done so far this year has been about designing, and primarily the designing of the data model. What entities are defined, how they're represented spatially, their attributes, constraints, and metadata. So that's mostly what we've been talking about, or I've been talking about this so far. But there are other things that need to be designed, and this is what we're going to be going on to see mostly next year in teaching block 2. So there's the design of the system architecture, how the various software components and hardware components interlink to create a working system. There is the design of program logic, Now, some of that comes into things like the logic, the constraints, for example, in a data model, and the cardinalities are examples of logic being implemented within a database environment, but there's also the logic that goes behind the interfaces and any programs that run on top and access data in the database. And then there's the design aspects of the user interface. How do we design good user interfaces, optimal user interfaces? So there's a whole variety of places and things that involve an element of design. So, development methodologies. These are formalized approaches for developing software systems, which, and a database is just an example of a software system. So part of what I'm going to talk about is this development methodologies. They're relevant both to designing a database, but also to the whole edifice that you're building, including interfaces and everything else, system architecture and everything else. It encompasses both the design of the system, those various elements of the design, and its implementation, what you could call the software life cycle overall, perhaps. And models specify stages of the development processes, what you do at the various stages, the order that they're carried out. Now, I should have tried to find some evidence for this, but people say the model followed can have an effect on the project outcome. It would be nice to have a good reference there to prove the case. So we need to look one up and see if we can find a good reference that identifies and quantifies how, or at least qualitatively evaluates how the chosen developed model affects outcome. So here's our simple waterfall model. If you remember, it originated in the mid-1950s, second half of the 1950s, early 60s, when the first software was being designed, and it was borrowed from manufacturing engineering workflow models. Very simple one. Find the requirements. We decide whether it's feasible to undertake to build the system, given the requirements. Presuming it's feasible, we go through a design process. Once we've got a design, we construct it. We can build our physical model, our physical system. We then test it. We then roll it out, implement it, roll it out to the users, and then we review what the users, take a review of the system. Is it working as desired? Is it working sufficiently well? Are there changes that need to be done? Very simple, linear model. Where you've come into the you've come in on, you're doing design and construction in your assignment. Yes, your database assignment. So basically, feasibility and requirements have been done. That was your briefing document. I mean, there may be lots of ambiguity, and it's a pretty basic brief. Feasibility, well, we decided we've employed you to build the database, so presumably we think it's feasible. So you're doing the design and the construction stage at the moment. You may well, of course, be doing some testing as well. Yeah, well, to a certain extent, I would say the testing's a proof of concept, which is kind of part of the design. Is, where specific things go in these things is debatable, and as we'll see on the next slide, it's all a bit more mushy than this. This is incredibly simplistic view of what happens. But yes, I mean, are the queries that you're writing, well, they're testing that the design is meeting the requirements. Now, the thought here is, in this model, is that this is user testing, but of course the developer, while constructing the system, is undertaking tests of the system as it's being built to make sure it's being built correctly. So this is more user testing, and probably as part of the construction and the design is the developer ongoing testing of what the developer's writing on a day or weekly basis, I would say. Does that answer the question? Yeah. There are lots of different models. The waterfall is probably the simplest and the oldest model. And since the waterfall model, lots of other software models have been developed. And I'm just going to introduce you to a couple of them. It's not something I'm any expert in. So here's a sort of a development of the waterfall model called the V model. V for verification or validation model. So this is basically the waterfall model, but with formal testing added on top. So we start with BRS, business requirement specifications, it says here. Of course, the terminology differs depending on who's writing the paper, where's it come from. So the business requirements, followed by the system requirements, which is basically the business, so you're getting more detailed. So this is the requirements of the users of the business. This is then translated into specifications for the system, high-level design, lower-level design, coding. You get some code. Code here could be database for you. A database is a form of code. Then you undertake testing. You can test individual units of code. You can test whether the components, the lower level design components, work correctly. Integration testing between the higher level components. Overall systems testing and acceptance testing. Does the system deliver what the users require? And as you can see, this is an ongoing process. So when the business specifications are originally devised, they need to be tested. They need to pass the acceptance test before you can move on to develop the systems. Test the specific systems requirements. They need to be tested before you can build the high-level design. That needs to be tested, etc., etc. And once when you've got your code, then you need to test your code at the various hierarchical levels. So does your code meet the unit test? So it basically, waterfall model plus formal specifications, testing specifications as to whether you've met the specifications at each stage or not. Here's a third one. This is the iterative development model. Also might be known as cyclic development model, probably has other terms, similar terms as well. So under this methodology, is that recognizes the fact that software development is often a cyclic process. It says the linearity of the waterfall model just doesn't represent the reality of what we do or how we go about building things. And it more happens like this, that we have a problem. So we design a system, a basic system, what they call a prototype here, that addresses some of the problems, some of the issues. We then take that basic design, simple design, test it, get users to use it, see what they like, see what they don't like, try it out. Then on the basis of the testing, the evaluation, you refine the model, the prototype, then you evaluate your new refinement in the light of the user requirements, create a new design, etc., etc. So it's recognizing that you're slowly getting incrementally towards the solution by iterating around this loop, going round and round this loop. We'll meet prototypes again. So if we take the waterfall and the iterative model and stick them together, they probably represent a broad brush overview of what actually happens in many software development models. The idea is, yes, you do have a linear section, you have an idea, something you're going to develop, but the reality is that you kind of go round in circles while you're doing it. That's a vague attempt to take an artistic picture as a sort of metaphor for what's going on. You have a linear section, but you're also going round and round in circles as you add development to it. So there are many, probably every single textbook that you look at, every paper that you look at about the waterfall model has a different diagram of the waterfall model. Doesn't make a great deal of difference as far as I'm concerned, not being highly concerned about methodologies and the minute differences between them. They basically cover the same steps, it's just whether you divide them, how you divide them more finely, basically. So what I'm going to do is run through this waterfall model. Look at each of the sections, see what goes on in them. Notice in this example of the waterfall model, we have the feedback loop from evaluation that takes us back to database planning. It recognises the cyclicity of the development process. So the first step in this model, I've seen often this is divided into two, a planning stage and a feasibility stage. I've seen that divided into two stages. In this one, it's just in one section, planning. So this is deciding basically whether you want to build a new system or not in the first place. So you need to decide whether it's worth building a system is first of all to identify the strengths and weaknesses of current systems and standards within an organisation, whatever it may be, whatever the organisation may be. Does the existing system meet the requirements? It may be that the new requirements are actually met by the existing system. Maybe it needs a bit of a tweak to do so. So don't assume you need a new system just because you've got new requirements. You may need a new system, or you may need to, it may be beneficial to tweak an existing system. So you need to know how the present system, if you've got presumably you've got a system in place, is meeting user demands, user requirements. At this stage, you should also consider how the world has progressed since the system that you're currently using was implemented. Are there new and revised standards, for example, since the system was developed? Many large corporate systems can be in place for 20 plus years. So in that period of time, the world of computer science has clearly moved on a great deal. There may be new standards, new software, et cetera, available. So one has to consider the existing system and how that system sits in the wider context of standards and data availability. So from that, you decide kind of what basically we don't get far as that, deciding what the system is. That's the next step. So we could revise standards. The other thing is, at this stage, we want to know really whether it's feasible for us to implement a new system. A new system may be a good idea, but it may not be possible to do it within the environment that you're working. So one of the issues is, under feasibility, there are 4 identified issues. Technological. Do you have access to the equipment, the technological equipment required to deliver the system? The servers, the software, etc. Do you have the skills in your staff force, your workforce, to undertake this development? Are you going to need to outsource the work? So there's technological hurdles. Operational hurdles. Is it possible to integrate the system within the present working practices of the organisation? Implementing new IT systems can be hardly problematic within organisations as it changes people's jobs, what they do. It changes their power relationships, who has access to information, for example. So when I worked my first ever GIS job, building a database for the water mains in Edinburgh, A lot of the information, knowledge about where water mains were and how they connected to each other was kept in the personal notebooks of who were called the water officers, who looked after a particular area in the city and were responsible for managing the daily supply of water to individual houses. They were the guys who said, turn that valve here now, because that will cut the supply off to this road, or provide the supply from a different direction. And when we were implementing the GIS, obviously we need to get the information out of these people's effectively private notebooks, out of their minds and into a public GIS service system, and that resulted in taking away some of the power from the water officers. They had that private knowledge, and that gave them power over how they operated within the council at that case. Now, it turned out that there wasn't particularly a problem. There was some grumbles to start with, but once they realized the benefits of having the good quality maps, then they started to realize that they would gain through the giving and the sharing of their information. They would lose something, they would lose some control, but they would gain something in the overall quality of information to allow them to do their own job. Clearly, there are economic issues. Any system requires finance, or at least time. So have you got the money to implement the system? Not only obviously to pay for things like pay for technology, but to pay for staff, or to outsource the material, the system development. And then there's things labelled sort of institutional constraints, things like, have you got management support, things like that. How would implementing the technology impact on the institutional structure, the organisational structure within, or the sort of structure within organisations? So presuming we think the system's feasible, we've got the money, we've got the resources, we then move on to, and we understand the existing system and have identified holes, missing, things that can be improved in the existing system or are not delivered by the existing system, we can move on to actually defining what this new system is going to actually do. So in the system definition stage, we identify the business scope of the database application. What's it going to do? Major application areas, identification of groups of users, who are the users of this system, and how it might interface with other information systems in the same organisation. Basically, a conceptual model plus a bit more. As I say, things like user groups. This is basically your conceptual model stage. I'm going through these very quickly. If you're interested in more detail on these, go and find a nice textbook. I think the recommended course text with the database, I can't remember, it's Connolly, isn't it? It's got a good breakdown of this. Okay, so we now know what we want to build. We've got a good conceptual model, a good idea of what kind of thing that we want to build. Then we go into a requirements section that says, well, we want to build this, but what do we need to build it? What are the requirements? What are the bits and bobs that we need to do? So we need to know more about where data is stored within an organisation, what formats it's stored in, who has control over those information resources, who's the owner of the information resource. And ownership within organisations can be problematic. In theory, often all the information is owned by the organisation, but the reality is that it's managed and has sort of individual ownership or custodianship by individual or groups of staff members. So in theory, everything I do, all my teaching materials that I prepare as a university lecturer are owned by the university. But I also have a personal stake in it, so they're both owned by the university and me, and it's a sort of slightly grey area actually who owns the materials I produce to teach, for example, these lecture slides. Does the university own them or do I own them? Well, we both kind of own them. That's a bit odd, a bit at university, but if you're thinking about charitable organisations, there may be similar things, individuals collecting, crowdsourcing data for charity organisations and things like that. Is the data collected in a crowdsourcing effort belonging to the individuals who collected that data or the organisation who organised the data collection itself? And of course, next term we'll be looking into VGI data and considering it in a bit more. So we go into greater detail on individual user requirements. Basically, we're focusing down on our system definition to the individual components within that system definition. Do we have the software and hardware available on site? Does it need to be upgraded? That kind of thing. Is all the required information or data available across the organisation? Often you find that data is not actually in the format that it might be, that it's most usable. And if not, how might that be collated? So, in the water department in Edinburgh, over the years, now let's see, it's quite a few years ago now, but if I count them up in my head, we probably had 5 or 6 different sets of maps showing water mains in Edinburgh at a range of scales, drawn at a range of times. Paper maps. This is the day we all had paper maps. It was moving into GIS. So, for example, in the centre of Edinburgh, there we had 1 to 500 maps, so quite detailed maps, dated back, now let's think, it was pre-county series, so they probably were drawn in about the 1920s. So the buildings on the base map were Edinburgh in the 1920s. But we used those on a regular basis because they were such high, good scale for working. You could see the pavements and everything like that. And quite a lot of Edinburgh hadn't changed since the 1920s, especially the centre, the old town. I don't know whether you're familiar with Edinburgh, the old town, the new town. It's a very old, it's not a modern city in the centre. So those were used on a daily basis in the city centre. But I think in the 1960s and 70s, for example, there was a second set of maps drawn on modern ordnance survey maps, printed out on sepia film that you had to scrape off with a scalpel and then draw with rotary ink pens. I was the worst at that ever. It's totally useless at that manual map updating. So that was drawn at roughly 1 to 2,500 scale, which is the master map scale from that period. Those maps had been updated in the 70s and were kept roughly up to date, but they were a lot poorer resolution. They were more than twice the scale, or half the scale. Then there were other ones drawn up probably in the 1960s, which were at a different scale. Plus they were all the notebooks of the water officers, plus all the engineering plans for when various things like new water mains and valves and systems at junctions were implemented. So we had this information, and in theory we had most of the information about most of the water mains overall, but it was scattered across all these information sources. So one of the big jobs that we had, or I had, was to assess how good these maps were so that we could come up with a data collection approach that resulted in the best possible solution from these multiple sources. And that is all very well, but then you're balancing the cost of collecting the data versus the benefits of having the data collected in the first place. So if we're contracting out, we were contracting out the data digitization, but we had to provide the instructions for the digitizing company as to how to get the data off the maps. Do they take the mains of the 1920s 1 to 500 maps, then add the stuff that isn't on there from the later maps? Or do you digitize the later maps and then perhaps use the 1 to 500 scale to improve the location of the mains in relation to things like curb lines to get actual good distances, correct distances? Do you do that? Do you pay an outsourcing company to do that? Maybe they're digitizing it in, there was a whole phase of offshore digitization. It was being done in India, in Indonesia and places like that. Do you trust an offshore digitizing house to be able to interpret your maps of Edinburgh that you looked at for years and looked after for years? Can you provide suitable instructions for people who've never seen the city and know very little about water mains as to how they should capture that data? Or is it best, should we just do a quick capture and then deal with all the individual issues, the updating, the details when we need it? So when we need to know that the water main, how far that water main is from a curb into a road, do we wait until we need to dig that water main up and then we go back to the original records and try and update the GIS? So quite a lot of consideration on a large data capture exercise or in a system requiring large data capture, then this can be extremely important. The cost of data capture is often, or can be, much higher than the cost of implementing the system itself. One should always remember that. So it's something that needs to be carefully assessed if any application you're involved in requires the capture of large amounts of information, digital information. Okay, we've sorted out our data. We know where our data is. We know what our users want. The next stage is to actually design the system. So we're now into the design section that we've mostly been talking about. So we're familiar with this. We develop the design that supports the objectives and the operations of the system. You do your logical design, ER modeling, class diagrams, etc., etc. Obviously, we've been only really considering the database design, but if we're talking about building an interface on top of that, that would also involve design of the interface at this stage, or may at least consider design of the interface. They have it as the application. The interface design is more in the next stage on this particular diagram. So we also need to, so having done the logical design, we need to start implementing the physical design, and that requires the selection of an appropriate database management system and the implementation of the logical model in the database management system. So how do we go about selecting a database management system? Well, clearly the first decision is, what kind of database do we need? Do we want a hierarchical database, a network database, a relation database, or an object-based database? Now, as I said the other day, or originally said, you can implement any database model or any schema in any of these database models. It's just that some are more suitable than others for the particular problem. So it's about choosing the most suitable model given the requirements of your system, also the availability of staff and things like that. While a network model may be using something like one of the new network databases, just escaping my Neo4j, it seems to be the network database at the moment. Do you want to, maybe you're working with networks, things like water mains, electricity companies, but do you really want to take that conceptual leap or that technological leap from a relational database implementation of a network model to a network database implementation of a network model? It's a whole new concept, whole new staff developers have to develop whole new concepts and understanding of how the data and the databases operate. So the optimal database model may not be optimal given the organizational requirements and the organizational context within which you're working. Then, of course, there's the functionality of your database management system. They all vary. I mean, most relational databases, all relational databases do the basics of the relational model. But they differ all in their ability, the add-ons that have been written, the extras that are available, topology, for example. I'm not sure whether there's a topology suite for MySQL database. I would have to look into that. But I know that there is one for PostGIS. But I also know that the PostGIS topology add-on has some problems. It's a project in development. So does it provide the functionality that you require to the degree you require? Is it stable enough? Does it support GUIs? Or have you got to develop GUIs using other software? So things like Oracle database comes, a commercial Oracle package comes with a whole lot of forms. You can build forms. They have an Oracle form system that allows you to build a data interface directly using the Oracle GUI functions. You can also do that with Access, but you can't do that with Postgres. I'm not aware of there being an add-on for GUI development in Postgres. There might be, but I'm not aware of that. Also, things like help wizards and help information in general. If you choose a database which is maybe free but has minimal documentation, clearly that's potentially a limitation in using the system, especially if you've got a turnover of staff and people have to learn, and a lot of that information and knowledge is in somebody's head. Query facilities, performance, those are other issues that need to be considered. Maybe you want to establish for performance some kind of bench testing to see. Bench testing is basically where you set up a test and see how well the computer system performs to decide which database management system is the most appropriate. Obviously, there's cost implementations, not only the purchase of software, but also maintenance, operational licenses, installation, training costs, and the cost of converting existing data. And I've said already, that can be huge. It can be an order of magnitude greater than the cost of actually building the database and the interface on top of it when you're talking about large amounts of complex data. Then you may be interested in things like portability. What hardware platforms does it run on? Are there particular network protocols that need to be that are required for the database to run? What programming languages does it support and can be integrated and can be used to access the data in the database? And we'll be talking about that kind of stuff again next year. So we've now chosen our database. We've built our database. So now we're thinking about, so we've now got an operational database, basically. It may not be rolled out to the users, but at least it's on the developers' machines, the developers' servers, and we can start thinking about the applications that sit on top of the database. Now, of course, the reality is we probably thought quite a bit about the applications earlier on in the design process, but you know, this is a linear system with stages, with actions in various stages. So we think about the graphical user interface. Now, of course, as I say, keeps on repeating. Next year we'll look at graphical user interfaces. But generally, the principles that you follow in graphical user interface design are things like the structure, how the fields and menus are arranged on the page, trying to keep it GUIs as simple as possible. Complex GUIs are not easy to use. The visibility of various items, selections and query, the tools at various times, what tools are visible at various times. How to provide feedback to the user, perhaps when they're doing something wrong. Mandatory fields is probably the simplest thing. How do you tell a user that they're entering the wrong information into a field? Tolerance, I think that's how perhaps resilience, how stable it is, perhaps. Can you reuse your GUI? Can you build components of a GUI that then you can reuse in various applications? So you have a small, what we might, sometimes they're called widgets. You develop a little mini GUI that allows you to do a certain action, but you might insert that widget in various bigger GUI pages. Yeah, so it's a smaller component of a graphical universe. And we'll look at all these and think about that next year. And then a list at the bottom there of various things that are sort of more specific rather than these general principles. So meaningful title for systems and menus, comprehensible instructions, logical grouping and sequencing of fields, visually appealing layout, intuitive input fields, icon labels, consistent terminology, abbreviations, suitable use of color. So all these things are practical ways of implementing these principles. The other thing in the application design that's increasingly important is not only design of the graphical user interface, but the development of and design of application programming interfaces. Is everybody happy with APIs? Yeah, no. An API is, and we'll meet these next year, are basically ways that a user or a computer can access data stored in a database, usually across the internet. So you publish an API, an application programming interface, which allows the other programs, and indeed people, to write web addresses, to use a web address with query components that then gets fired to the database, and then the database returns you a set of data that you can then use in your application. So this is about interoperability. So basically it's a sort of computer-based interface that allows you to chuck queries at a database and get the data returned to any particular application. So many applications now, you tend to build an application programming interface, and then you build your applications that use this interface to communicate between systems. Much more about that next year. So we've got a basic system. We've got a database, and we've got some applications built on top. Now, while we're developing both the database and the application design, well, the application is obviously picking the data up from the database, is that it's often a good idea to have some kind of prototyping involved in this. Developing a working model of some or all of the database application and the user interface on top of that. There is no requirement for a prototype to be a prototype of all functionality. It could just be a small subset of functionality. What you might call a sandbox application, something that you build with the intention of throwing it away and not using it. It's just a temporary structure, but you can test and play around with things, see what the users like, see what they don't like, before you fully release the system. Very useful where extensive development is needed. This is often where the reality of the discussions between users and developers that happen here, that result in a plan, this is where the chickens come home to roost, so to speak, and the reality of whether the design that you came up in the first place is actually a good idea. Perhaps next week I'll tell you, well, I will. I'll tell you next week about some of my problems I've had with the disconnect between the plans and the great ideas of the great and good and the reality of implementing stuff. It provides a quick and cheap means of testing. You don't want to invest huge amounts of resources and effort in building a fully all singing, all dancing system that you planned from the beginning to then discover that you've got some fundamental flaw buried deep within inside it. Better to do some prototyping, identify any flaws with a minimal effort before integrating that into a final system. So as I say, it helps clarify system requirements and possibilities. Prototyping, this is just a little diagram showing the prototyping system, pretty obvious. It's a mini version of the full development cycle. You design a prototype to meet a particular set of requirements or to test a particular set of requirements or set of processes. You build the prototype, you use and test it, you review it, you decide what to do with it. Now, some prototypes you just chuck away. Maybe because they were just, as I say, these sandbox test beds just to test little things out. But often prototypes slowly develop into fully functioning systems, or at least subcomponents of systems, which can then get plugged into the full development system, into the actual system. So very, very straightforward. We have a working database. We have applications on top. We need to roll it out to the users, or at least this is not actually, the rollout isn't quite here yet because we haven't gone the voting and loading. This is, in this model, in this version of the waterfall model, the implementation section is basically the finished, or I understand it as the sort of finished product of the design, the database design, the application design stages. So it's the final realization of the system before release to the users. So the creation of the final empty database schema, loading a subset of data in here to test out that it's working properly, updating existing clients, programs so that they plug into it. User training starts at this point so that the users understand the system. I must admit, I find this rather fuzzy, some of the divisions between these stages. They are slightly fuzzy, I find. Then, once we've got a fully working system, then we need to get the full data into the system. You don't want to load the data all the data into this system here while you're still building and designing it, because it's a big effort to load large amounts of data. As you may have discovered, you may need to redesign your database design, and that involves either moving data within your database, or just reloading and starting again. So it's often a good idea, if you're working with a large data set, to just work with a subset of the available data. So you transfer your existing data in, from digital data, also data digitized from page-per records, perhaps, and then you QA test the data loading for data load errors in system logic, GUI usability again, making sure. Because what the GUI usability and the database functioning may be fine with your small subset of data, you load in 100 times more data, you may have performance issues, clearly. Evaluation, survey the users to determine the application satisfaction. Decide what to do about it, particularly the information available and how it's presented. And then the various actions that you might undertake at this point, having examined what the users think of the final system. Sometimes it just requires improving the documentation that's provided to users. Also, obviously, improving training. It takes time for people to use new systems. Documentation helps, training helps, obviously. But there also it might pick up actual changes in design that are required, that need to be fed back into the design planning stage. Hopefully, these design changes are not sufficient that the system is unusable, but they can be. As we know, a lot of IT systems fail. And one of the problems, I think, is that if you don't specify, one of the main problems we know is that if we don't specify the requirements well at the beginning, then when it comes to evaluation, you may have built not exactly the thing that's required in the first place. I have personal experience, I'll tell you next week, about lack of planning lack of deciding what a system's going to do, leading to a failure of a software design process, or at least a semi-failure. We've got the system. We now roll it out to the users, but we need to still look after the system. It's not like the system, the design, that we've finished with it. We need to maintain the system, backups, recoveries, things like that, but also what we might call adaptive maintenance, making sure it's still running correctly, auditing performance, playing around with tuning to improve performance, making sure that security is kept up to date, etc., etc. And that's what the sort of second half of the today is going to be about. And we'll take a break in a minute, but we'll just look at these lists of roles. So obviously we talked about personnel, lots of personnel involved potentially in large database systems. So I thought it might be handy just to chuck up 2 slides so that about job roles and things like that. So the database administrator is the person in overall responsibility for the management, often of data resource and the database application. Not, when I say management of the data resource, I'm talking about management within the computer system rather than management from the sort of field data collection perspective, perhaps, which tends to be organized by domain experts, planning officers, environmental scientists, whoever's collecting the data. But they're often responsible for the management of the data resource within the database, and also the application, the database itself, and any applications potentially sitting on top of the database. So they're responsible for planning and development, conceptual logical design, physical design and implementation. Often, of course, they don't do all these roles themselves. They're managing these people doing these jobs. But they should know about things, particularly of things like maintenance of standards, policies and procedures, I would say. Making sure that security settings are adequate for the database. They're responsible for looking after that data resource. So if they haven't implemented correct accessibility and security issues, then they're not doing their job. And also overall monitoring system performance. So the database administrator is the main person looking after the overall management of the database system. But you might see all sorts of other roles advertised or as part of a job description. So you may see system modelers being a job for a system modeler or system designer. They use all different terms for these. And a system modeler specializes in conceptual design. They specialize, and to a certain extent, logical design, I should say conceptual and logical design there. So they're specialists in talking to people, talking to users, and deciding what systems should do and coming up with the sort of logical and conceptual designs of systems. So they're specialists on that. They're not specialist computer programmers, although they often clearly have a computer background, but they're very good at talking to people and communicating and bringing ideas together and arriving at consensus. So it's it's quite a human-related system, but also modeling the objects and the entities and things like that. Then you have what might be called a database designer. They're much more of a hardcore coder, physical design and implementation of the database, particularly on a database side. Often designers, developers, programmers specialize in databases or what you might call as more general programming. So you've got database designers, specialists in implementing the databases. We might have application programmers. These are the people who implement the programs that perform operations on the database, the ones who look after the client programs. The experts for things like graphical user interface development and things like that. So these different roles in the design process are often taken by different people, especially in large computer systems. Basically, these people make up the team that build the system. And then, of course, we've got these end users. Many jobs, as you've probably seen out there, now advertise town planner with GIS or with GIS experience, environmental scientist with GIS experience. And we can broadly classify end users into two types, what we might call naive users. These are people who don't care about the underlying database. They're simply there to use the application. A checkout operator might be an example. I'm sure a few checkout operators are highly interested in the systems that they're using, but it's not required for their job. They just use the system. They're the people who press the button, so to speak. But then you also have sophisticated super users, familiar with database management systems. They have an interest in database management systems, and they can even sometimes design their own applications if they have a programming bent. These are usually domain experts. These are the people you really need to get on board in system when you're developing systems. These are the people who will spend the time to talk to you about their user requirements, about the system requirements. And it takes a long time and a lot of talking often to understand user requirements. And super users, they are also great ambassadors for systems. As I say, sometimes when you implement a new system into an environment, people's roles and jobs change. That can be threatening to people, which doesn't lead to a happy workforce. Super users are often a good bridge between the people saying we need this new system and the people whose jobs are going to change as a result of it. They have that knowledge both of the system and also of the domain that they're working in. All right, we'll take a break and then we'll go into the world of efficiency and improving. So, any questions on that first half? Sorry, it's not the most